Oh, hi, hello everyone, and welcome to our lesson on the periodic table of the elements. Uh, we obviously we have a lot of ground to cover in this topic, so I'm going to try to go in small steps so it's not too confusing. Let's start at the beginning. Well, here we go, the periodic table. Obviously, the first question that many people would have when we start to study elements is, what is an element? What actually is an element? Well, an element is a substance that only has one type of atom. It can't be broken down into several different types of atoms. To give you an example, water. We know that a water molecule can be broken down into one oxygen atom and two hydrogen atoms. That's why water has that formula H2O that we are all so familiar with. So water is not an element, but the hydrogen and the oxygen are elements because we cannot break those two things down into other elements. Here on slide 3 we see a list of several elements. Many of these you probably know. Chlorine, nitrogen, silver, mercury. You can read through the rest. Okay, so here, let's go on to slide 4. So where did this idea come from? Why did we first develop this idea that the world was made up of elements? As far as I know, this first comes from a guy named Aristotle. Aristotle believed that the world could be broken down into simpler things. You see, his theory was that the world could be broken down into air, water, fire, and earth. For example, if you took a piece of wood and you burned it, you could see flames coming out of the wood, so there was fire. You can see smoke coming out, so there's air. After the wood burns, you're left with ash, which is the earth. So Aristotle looked at that and he said, the way wood burns, you can see the wood breaks down into fire, air, and earth. Obviously, he was incorrect, but this idea that everything can be broken down into simpler things was correct. Since then, we can see scientists have identified 90 naturally occurring elements and created about 28 others. Those 28 elements that scientists have created are all very heavy elements, and they are at the end of the periodic table. Down here on slide 2, you can see this bottom row starting at about, starting down in the hundreds. All of these elements down on the bottom row have been created by scientists. They are not found in nature. Here, let's go on, slide 5. The elements alone or in combinations make up our bodies, our world, our sun, in fact, the entire universe. Right. Everything in the universe is made of those elements or some combination of them. Here on slide 5 we have a picture of a galaxy. A galaxy like this is going to be mostly hydrogen and helium gas, with trace amounts of some other elements as well. Let's move on. Slide 6, the most abundant element in the Earth's crust is oxygen. That means there is more oxygen in the crust than any other element. You have an illustration of that here. The oxygen is the blue. We can see 46%. The next one is silicon with the yellow, 27%, then aluminum, iron, and calcium. One reason that there is so much oxygen in the crust is that oxygen forms many compounds with other elements, like silicon, iron, and magnesium. So we're going to actually talk about that later in the presentation. We are going to see why oxygen forms compounds with these metals like iron and silicon. But let's move on to slide 7. The periodic table. That's that big table that we saw at the beginning of the presentation. The periodic table organizes the elements. And the way these elements are organized can give us a lot of information. You can actually tell a lot about an element by where it is in the periodic table. And we're going to talk later about how we learn that. For example, you can predict with reasonably good accuracy the physical and chemical properties of the element. The physical properties, let's talk about those. Physical properties would be what's the color? How hard is it? Is it a solid, a liquid, a gas? All of these things are physical properties. Chemical properties refers to how it behaves with other elements. What kinds of compounds does it make? What other elements does it react with? What elements does it not react with? All right. Understanding the organization can help you get basic information about each of the elements. All right, terrific. Let's move on. Okay, let's start here. Elements are organized on the table according to their atomic number. Let's actually go back quickly to slide 2. You can see there it is. If we start in the upper left-hand corner, you can see hydrogen. And as we move across, we find to helium, number 2, then back to lithium, beryllium, boron, carbon, nitrogen, oxygen, and so on. They're just listed from left to right, top to bottom, just like you read lines in a book. All right. Now that atomic number is usually found at the top of the square. Notice hydrogen's atomic number is 1. The atomic number refers to how many protons an atom of that element has. So hydrogen has 1 proton. So hydrogen is has the smallest nucleus, and it is the lightest element. For instance, hydrogen has 1 proton, its atomic number is 1. Now, most of the time, elements like hydrogen will have the same number of protons and electrons. So hydrogen, for example, with 1 proton is also going to have 1 electron. Now, we also know there is another type of particle in the atom. We know the proton has a positive charge, the electron has a negative charge. We also know that third type of particle, the neutron, which has a neutral charge. there's nothing in that square that tells us how many neutrons, because that can actually change from element to element. For example, hydrogen will always have one proton, but it might have one neutron. It might have 0 neutrons. And we're actually going to talk a little bit more about this later. So we'll come back to that. No two elements have the same atomic number. No two elements have the same number of protons. They may have the same number of neutrons. All right, so here we go. Moving on, what's in a square? We can see the atomic number, which we've talked about, the symbol, which is usually 1 or 2 letters. Right underneath the symbol, we see the atomic mass. That's the average mass of the element. And here the name of the element and the state of matter at room temperature, standard temperature and pressure. Hydrogen we know is a gas. We see gas in the lower left-hand corner. Let's move on. The atomic number refers, again, the atomic number refers to how many protons. No two elements have the same number of protons. Hydrogen always has 1 proton. Helium always has 2. Lithium always has 3. Any atom, yeah, okay, so I think you've got that. Let's move on. Atomic mass, remember, this is the number that's right underneath the chemical symbol. So in the case of hydrogen, it's this number down here, 1.000794. The atomic mass refers to the weight or the mass of the atom. It is derived by adding the number of protons with the number of neutrons. So here we have an example in the case of helium. In this case, we have an atom with 2 protons and 2 neutrons. So the atomic number would be 2, but here the mass would be 4 because we have 2 protons and 2 neutrons. Atomic number would be 2, the atomic mass would be 4. Okay, let's move on. Here we go. Now remember, I told you that for an element like hydrogen or helium or lithium, the number of protons is always the same, but the number of neutrons can change. The number of neutrons is not always the same. You can see an illustration of this on slide 13. In the first row we have hydrogen, and there to the right we see 3 different isotopes of hydrogen. We see hydrogen with 1 proton and 0 neutrons. Next, 1 proton and 1 neutron, and then last 1 proton and 2 neutrons. These are 3 different isotopes of hydrogen. Notice the number of protons is always the same. The number of neutrons can change. You see the same thing there with helium and lithium. Again, helium always has 2 protons, but can have 1 or 2 neutrons. Lithium always 4 protons, always 3 protons, but can have 3 or 4 neutrons. And I want to look at the last point. An atomic mass number with a decimal. Remember, our atomic mass for hydrogen was a decimal. It was like 1.000794. That's the total number of protons plus the average number of neutrons. So we're dealing with an average there. That's why you have the decimal. Most of the time, hydrogen will have one proton and no neutrons. But hydrogen can, on rare occasions, have a neutron. That's why the mass number is pulled up slightly above 1. Okay, let's move on. The atomic mass unit. The unit of measurement for an atom is AMU, atomic mass unit. It is equal to the mass of one proton. All right. There are 6.02 times 10 to the 23rd AMUs in 1 gram. 6 times 10 to the 23rd, or we sometimes say 6.02 times 10 to the 23rd. This is a very important value in chemistry called the mole. It's the relationship between the mass of a proton and 1 gram. I know it's kind of hard to imagine this number, but to give you an example, in the human body, like my body or your body, there are about 100 trillion cells. Now, on the planet Earth, there are 7 billion people. So 6 times 10 to the 23rd would be about 100 trillion times 6 billion. So 6 times 10 to the 23rd, that's about the number of cells in all of the human bodies on the entire Earth. If you can try to wrap your head around a number that large, that's what we're talking about when we talk about the mole. All of the cells in all of the human bodies on the planet. And the next point there, remember that electrons are 2,000 times smaller than an AMU. Electrons are much, much smaller than a proton or a neutron. Symbols. Slide 16. All elements have their own unique symbol. It can consist of a single capital letter, like carbon is C, and 1 or 2 lowercase letters, like in copper, we have Cu. I know sometimes these symbols can be a little confusing. You might say, I understand carbon, C for carbon, but what about these crazy symbols? And let's go back and look at the periodic table very quickly. What about gold is AU? Why not G or GO? Mercury, number 80, is Hg. Why not Me or MER? The reason for this is that a lot of these symbols come from Latin and Greek names for these elements. Let's see if I can give you an example. All right, nothing's jumping out at me, but all right. So yeah, a lot of those chemical symbols come from other languages, from Latin or Greek. So that's why sometimes they don't seem to make any sense. Let's move on. Here we see a few common symbols, nitrogen N, but again, potassium is K. It's because it's from another language, not English. Sodium Na. Nothing like the English name. You just have to get used to them. Okay, let's move on. The valence electrons. Um, Now we've learned that there are several different particles in the atom. We've learned about the protons, which have a positive charge, the neutrons, which have a neutral charge, no charge, and the electrons, which are much smaller than the protons and have a negative charge. Now, the protons and the neutrons are together in the nucleus. That's that green circle here in the illustration on slide 18. So most of the mass of an atom is in this tiny, tiny nucleus. And then the electrons are actually moving around the nucleus in these different orbitals. Now these electrons, they don't just orbit anywhere. They only can exist in specific certain levels. And we say that these are certain energy levels of an electron. I want to look at point number 2 here. Valence electrons are the electrons in the outer energy level of an atom. For example, let's look at those 2 atoms that are illustrated in the square on the right. We are only seeing the valence electrons. This picture, they did not draw electrons on the inner levels. So this element, we could have 1 or 2 levels underneath that one we're seeing. These are the electrons that are transferred or shared when the atoms bond together. So it's valence electrons that determine how an atom will react with other atoms, how an element will react with other elements. The elements of the periodic table can be divided into 3 main categories: metals, nonmetals, and metalloids. Pretty self-explanatory. It's illustrated right there. We are going to talk about each of these groups one at a time. Oh, there is... here, let's start with metals. Metals are good conductors of heat and electricity. When we make the wires, when we make electrical wire, we make it out of copper because copper is a metal. It conducts electricity. When we make kettles and cooking pans, we make these things out of iron and copper and other metals because they conduct heat very well. They get very hot very quickly. Metals are shiny. They reflect light. They are ductile. They can be stretched into wires. They are malleable, which means they can be pounded into sheets. A chemical property of metal is its reaction with water, which results in corrosion. Yes, most metals react very easily with water, and we're going to look at why they react later in the lesson. Here, nonmetals. Nonmetals are poor conductors of heat and electricity. Here we see sulfur. Sulfur is one of the worst conductors on the entire periodic table. They are not ductile. They are not malleable. They are brittle. They crumble. They break. They are dull. Many of the nonmetals are gases. Sulfur, of course, is not, but hydrogen, helium, fluorine, chlorine, all of these nonmetals are gases. Metalloids. Now the metalloids, they're that purple, these are the purple elements that make that, it looks like a flight of stairs going up the periodic table. You can see that easily on slide 19. The purple stairs are your metalloids. These are kind of in between the metals and the nonmetals. They have some properties like metals, some properties like nonmetals. For example, you can see they can be shiny or dull. Shiny like metals or dull like nonmetals. You can see in the illustration we have silicon. It is shiny. They conduct heat and electricity better than nonmetals, but not as well as metals. They're kind of in between. And silicon's a great example. Here, slide 23, elements in the periodic table are grouped into families, which are columns. Elements in families have similar properties. And the reason that they have similar properties is because elements in these families are always going to have the same number of valence electrons. They're going to have the same number of electrons in that outer energy level. Slide 24. The elements are also categorized into periods or horizontal rows. Elements in periods do not have similar properties, and that's because they do not have the same number of electrons in that valence shell. They don't have the same number of electrons in that outer shell. But they do have the same number of shells. For example, let's look at the first row, the first period, hydrogen and helium. Hydrogen and helium are both going to have 2 shells. Hydrogen will have 1 electron in that valence shell. Helium will have 2. Now, that first shell can only hold 2 electrons. So after hydrogen and helium, we go to the next shell, the next period, the next row. And we start here on the left with lithium, and we go across 1, 2, 3, 4, 5, 6, 7, 8. That second energy level can hold 8 electrons. So we have 8 elements in that second period. Notice we start here with lithium. Lithium has 1 electron in the valence shell. Its atomic number is 3, so it has 3 electrons. It has 2 in the first shell, leaving 1 in the second shell. So hydrogen has 1 electron, 1 valence electron, so does lithium, so does sodium, so does potassium, so do all of these elements in the first column. But they all have a different number of shells, a different number of energy levels. Let's move on. Here we go. Here on slide 25, we see some of the characteristics of families, those vertical rows that all have the same number of valence electrons, and then periods, those horizontal rows that all have the same number of energy levels. So here, families, columns of elements are called groups or families. Those are the columns, straight up and down. Elements have similar but not identical properties. For example, lithium, sodium, and potassium. We talked about them. Lithium, number 3. Sodium, number 11. Potassium, number 19. They are all soft, white, and shiny metals. We're going to talk more about that in a few slides. So keep that in mind, but we're going to talk more in detail about that. All elements in a family have the same number of valence electrons. If you take anything from this lesson, take that. Elements in the same column have the same number of valence electrons. Periods. Each horizontal row is called a period. They are not alike. They do not have the same number of properties. Properties can change greatly across a row. The first element in a period is always a very reactive solid. The last element is always an inactive gas. We're going to look at the different families. We're going to talk about that. Why is it that that first element in a period is always very reactive, but that last element down here, the elements like helium, neon, xenon, radon, why they are not reactive? We're going to talk more about that. So let's move on. Families. Here on slide 27, take a quick look at this and try to tell me what element is that's highlighted. The first element, that is hydrogen, atomic number 1. Here, underneath hydrogen, we have our first period. Look, let's just quickly go through all of them. Boom, boom, boom. You can see each family being lit up. Let's talk about that first. First, let's talk about hydrogen, atomic number 1. The hydrogen square sits atop family A1, but it is not a member of that family. Hydrogen is in a class all its own. That's why hydrogen was lit up on its own. It's a gas at room temperature, 1 proton, 1 electron, 1 energy level. It needs 2 electrons to fill up its valence shell, that valence energy level. So it already has 1, so it wants to gain 1 more. It needs 1 more electron to fill up its valence level. All right. First, let's talk about the alkali metals, the first family. The alkali family is found in the first column of the periodic table. Atoms of the alkali metals have a single electron in their outermost level. They have 1 valence electrons. They are shiny, they have the consistency of clay, they are easily cut with a knife. Alkali metals, this includes metals like sodium and potassium. Those are the 2 most common alkali metals. Because they have 1 valence electron, it's very easy for them to lose that 1 electron and form a compound with another element. So the alkali metals are very reactive. They react very easily with other elements. And we're going to see a little bit more about that in a couple of slides. Here we go. Alkali metals. They are the most reactive metals because they have 1 little valence electron. It's very easy for them to lose that 1 electron in a chemical reaction. They react violently with water. Here we see a picture of sodium reacting with water. Sodium will actually burn in water. That's how violently it reacts. They are never found as free elements in nature because they react so quickly, they always bond with another element. What does it mean to be reactive? We're going to talk a lot about reactions, so let's talk about what that means. Elements that are reactive bond easily with other elements to make compounds. Remember, we've talked about compounds before. We know that, for example, water is a compound with 1 oxygen atom and 2 hydrogen atoms. Salt is a compound. Salt is a compound we're going to talk about with 1 sodium atom and 1 chlorine atom. Some elements are only found in nature bonded with other elements. What makes an element reactive? Here, an incomplete valence electron level. The next point is what I want. The next 2 points are very important. All atoms except hydrogen want to have 8 electrons in their very outermost energy level. In that valence level, they want to have 8. This is called the octet rule. Atoms bond until this level is complete. Atoms with few electrons will lose them. Remember, like sodium and potassium will quickly lose that 1 valence electron, so that they now have, at the next lower level, they now have a complete energy level. We're going to see a picture of that soon. Atoms with 6, 7, or 8 valence electrons, like oxygen, will gain electrons during bonding. Here is a great example. Sodium. Remember, sodium's atomic number is 11, and you can see here that that sodium atom has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 electrons. So sodium's got 11 protons in the nucleus, 11 protons, and 11 electrons in these 3 different shells. 1 electron in the valence shell. Beside that, we have an atom of chlorine. Remember, chlorine's atomic number is 17, meaning that chlorine has 17 protons in its nucleus. And then around that nucleus, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 electrons. Notice we have 7 electrons in the valence shell. Sodium 1 valence electron, chlorine 7 valence electrons. Now remember, elements want to have 8. That's our octet rule. So this chlorine has 7. It's like chlorine has 1 space that it needs to fill. And that sodium has 1 electron that it wants to give away, so that it can have 8 in its outer shell here. So what happens? Chlorine has 1 space. It wants to receive an electron. The sodium has 1 extra electron. It wants to give that away. On page 43, on slide 43, we see what happens. The sodium loses that electron. It gives that electron to the chlorine atom. Now you see sodium has 8 in its valence shell, and so does chlorine. And that's a lot more stable for the atom. If it only has 1 in the valence shell, the whole atom is a little bit unstable, but when it loses that electron, we have a more stable configuration. Now remember, our protons have a positive charge, which we show with a plus, and our electrons have a negative charge, which we show with a minus. So now our sodium has lost an electron. So what is the charge like? Well, remember, we still have the same number of protons. We've got 11 protons. So that's like 11 plus. But now we only have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons. So that's like 10 minus. So we have 11 plus 10 minus. That's a total of plus 1. So we say that the sodium ion now has a plus 1 positive charge. The chlorine, remember, still has 17 protons in the nucleus. So that's like plus 17. But the chlorine now has gained an electron. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 11, 12, 13, 14, 15, 16, 16, 17, 18 electrons. So that's like 18 minus. So for the chlorine, we've got 17 plus, 18 minus, that's a total of minus 1. So we say that the chlorine has a negative charge. So our sodium has plus 1, or positive. Our chlorine has minus 1, or negative. Now remember what happens here. It's just like with magnets. Some of you know that if you've ever played with a magnet, we know that we have the north end and the south end, north pole and south pole. Now the north and north will repel one another, but north and south will attract. It's the same way with positive and negative charges. Two positive charges will repel, but a positive and a negative will attract one another. Well, now we have a positive sodium and a negative chlorine. So what are they going to do? They're going to attract each other. And they're going to form a bond. And that bond makes a new molecule, what we call sodium chloride. And you use this compound every day. It's just table salt. This is salt, sodium chloride. All right, let's move on. The next column, alkaline earth metals, they are never found uncombined in nature. That's because alkaline earth metals, like alkali metals, are very reactive. They have 2 valence electrons, and they will lose those valence electrons very quickly. And they will form ions like calcium. Very quickly forms calcium plus 2. Alkaline earth metals include magnesium and calcium, among others. Magnesium is also very reactive. Not as reactive as sodium. If you put magnesium into water, it will not go up in flames. It will not burn the way sodium does. But if you strike a match near a strip of magnesium, it will burn very, very quickly. It will burn very bright and very quickly. Let's move on. Transition elements include elements in the B families. These are the metals you are probably most familiar with: copper, tin, zinc, iron, nickel, gold, silver. They are good conductors of heat and electricity. A lot of these transition metals have one or two valence electrons, and they form compounds very easily with elements like oxygen. We're going to talk a little bit more about oxygen late in a couple of slides, but remember, oxygen has 6 valence electrons, so it wants to gain 2 more to have 8. These transition metals, many of them have 2 valence electrons to give away. So we have oxygen with our 6. It's ready to take those 2 valence electrons from a transition metal. That's why many of these metals, like iron and zinc, will react very easily with oxygen. The compounds of transition metals are usually brightly colored and often used to color paints. Yeah. Transition metals will form a compound. When they make a compound, they often have bright colors. We have a palette here. Just to give you a few examples, cobalt is a transition metal. That's often used to make blue paint. Cadmium is a transition metal used to make red paint. Zinc, which you are probably familiar with, often used to make white. Titanium, also used to make white. Cadmium, which is for red, in different compounds with different elements, it can also make yellow. So many of these paints right here on this palette come from our transition metals. Yeah, underneath. Transition elements have 1 or 2 valence electrons, which they lose when they form bonds with other atoms. Some transition elements can lose electrons in their next to outermost level. This gets a little complicated, but it's many batteries work on this principle. Transition elements have properties similar to one another and to other metals, but their properties do not fit in with those of any other families. Many transition metals combine chemically with oxygen to form oxides. We talked about that already. Next, let's move on to the boron family. Boron, atomic number 5. It's named after the first element, which you can see the picture right there on slide 49. They have 3 valence electrons. Remember, let's look at boron, atomic number 5. So 2 valence electrons in the first energy level, 3 in the second. This family includes the most abundant metal in the Earth's crust, aluminum. Aluminum is number 13. It would be right underneath boron on the periodic table. The carbon family, they have 4 valence electrons. This family includes a nonmetal, metalloids, and metals. Metalloids, like silicon, they are going to have properties of metals and nonmetals because they're kind of in the middle. Remember, metals are going to lose electrons very quickly. These nonmetals over on the right are going to gain them very easily, very quickly. The metalloids, they're right there in the middle. they can gain, they can lose, so they form these crystals. The element carbon is the basis of life because carbon is used in so many organic compounds like sugars. There is an entire branch of chemistry devoted to carbon compounds called organic chemistry. Yeah. Nitrogen, next. You've probably heard of nitrogen gas. It is the element that makes up 78% of our atmosphere. It also includes nonmetals, metalloids, and metals. The atoms of the nitrogen family have 5 valence electrons. They tend to share electrons when they bond. Remember, when we looked at sodium and chloride, we saw the chlorine takes an electron from the sodium. But these elements, these compounds formed from nitrogen, it's not about taking electrons, it's about sharing them. To give you an example would be ammonia. Remember, nitrogen has 5 valence electrons, so it wants to gain 3 more. Hydrogen has 1 valence electron, so it wants to gain 1 more. So nitrogen can actually form 3 bonds, or form a bond with 3 hydrogens, and they each share electrons. So that way, the nitrogen, the 3 hydrogens bring in 3 electrons, so nitrogen ends up with 8 valence electrons. And the nitrogen shares 3 of its electrons with the 3 hydrogens. So the hydrogen atoms all end up with 2. So by sharing electrons, they're all happy. So you have 1 nitrogen bonded to 3 hydrogen atoms, and that's ammonia, a very common organic compound. Other elements in this family are phosphorus, also a very important compound in organic chemistry, arsenic, antimony, and bismuth. The oxygen family, they have 6 valence electrons. Now remember, nitrogen has 5 valence electrons, and so it wants to form bonds with 3 hydrogen atoms to make 8. Oxygen has 6, so it wants to form bonds with 2 hydrogen atoms to have 8 valence electrons. So where nitrogen has formed bonds with 3 hydrogens to make NH3, oxygen bonds with 2 hydrogens to make H2O, which we know as water. Oxygen is the most abundant element in the Earth's crust. It is extremely active and combines with almost all elements. In particular, hydrogen and metals. But it also reacts very well with carbon to form a lot of different organic compounds like carboxyl groups and sugars. Next, the halogen family, extremely reactive elements. They have 7 valence electrons, so they gain, let's see what we got. There we go. 7 valence electrons. They only need to gain 1 electron to have a complete valence shell, a complete outer energy level. So they gain electrons very quickly, very easily. So they are very, very reactive, and they are almost never found in nature. These are elements like chlorine. They react with alkali metals to form salts. Remember, we saw that. The halogen chlorine reacts with the alkali sodium to form sodium chloride. So the alkalis lose an electron. The halogens take an electron. So these halogens react with the alkalis to form salts like sodium chloride, potassium chloride, potassium fluoride. Noble gases. They are colorless gases, extremely unreactive. This is because they have a complete valence shell. They all have 8 electrons, so they don't need electrons. They don't want to give any away, and they don't want to take any. So they stick to themselves. They're kind of loners. One important property of the noble gases is their inactivity. They do not react with anything else. They are inactive because their outermost energy level is full. They all have 8 valence electrons. The family of noble gases includes helium, neon, argon, krypton, xenon, and radon. They are all found in small amounts in the Earth's atmosphere. So they are very rare, but they do not form compounds. So they're all found in the atmosphere. The rare Earth elements at the bottom, the lanthanide and the actinide series. One element of the lanthanide series and most of the elements are called transuranium, which means synthetic or man-made. These elements are not found in nature. They've only been made by scientists in laboratories. Okay, so where did this idea of the periodic table come from? This brilliant way of organizing all of the elements by their chemical properties, by the number of valence electrons. It came from a guy named Mendeleev, a Russian guy, Dmitry Ivanovich Mendeleev. He created the first accepted version of the periodic table. He grouped elements according to their atomic mass, and as he did, he found that the families had similar chemical properties. Blank spaces were left open to add the new elements which he predicted would occur. An interesting thing about Mendeleev, he was not a professional scientist. For Mendeleev, this was just a hobby. So he was working on his own, and he just took these cards and wrote the names of the elements on the cards, and then he started putting them on a table by their different properties. And then he realized that if he put all these alkali metals here and all these noble gases here and then all these halogens here, that they would fall into nice little columns, and from that he could make the different families of the periodic table. Okay, we know matter. All matter is composed of atoms and groups of atoms called molecules. Substances made from one type of atom are called pure substances. One type of atom, these would be pure substances, are elements. If we just have pure oxygen gas, that's a pure substance. It's only one element. If we have a piece of gold or silicon or sodium, that's a pure substance because there's only one type of atom. Only gold atoms, only silicon atoms, only sodium atoms. Substances that are made from more than one type of atom bonded together are called compounds. Like water, one oxygen atom bonded to 2 carbon atoms. Sodium, salt, one sodium atom bonded to 1 chlorine atom. Compounds. They are combined. Compounds that are combined physically but not chemically are called mixtures. Let's look very quickly at that. So we're going to go back and look again at sodium chloride. Sodium is an element. There's our 1 valence electron. Chlorine is an element. There is our 7 valence electrons. Sodium and chlorine bond. They make sodium chloride. That's a compound. Now let's move on. We know that hydrogen is an element. Oxygen is an element. Hydrogen and oxygen bond. They make water. So let's look at those two compounds that we just talked about, salt and water. But when salt and water are combined, we don't make a new compound. Here we have sodium and chlorine to make NaCl. Here we have hydrogen and oxygen to make H2O. But when we bring together salt and water, we don't make some new compound called like NaH2ClO. We don't do that. We end up with a mixture. Compounds in mixtures retain their individual properties. We don't have a new compound. We still have salt and water. They're just mixed together. Mixtures can be separated by physical means. For example, to separate water from salt, we can distill it, which means we boil the water. The water will evaporate, the salt will not evaporate. So when the water will rise up, we can take the water from the salt. Compounds can only be separated by chemical means. Elements are pure substances. When the subatomic particles of an element are separated from its atom, it no longer retains the properties of that element. If you could somehow take a proton away from a sodium atom, remember sodium atomic number 11, it has 11 protons. If you could take one away, it would no longer be sodium. It would now have 10 protons, and it would be neon. And that's actually how they create new elements, by adding protons to the elements we already have. That's where those rare earth elements come from. All right, that is the end of our presentation. I hope you found this informative. If you're still confused, I recommend you go over, maybe watch it one more time, go through very slowly, slide by slide. But I know it's difficult to wrap your head around, but it can help you to. This can help you to understand the way everything in the universe is made up of these very simple substances, elements. All right. Okay, let's go ahead and finish. Thank you all very much, and I will see you next lesson.